Hi all, welcome to new class. Today's class is about the design of code converters. The code converters are logic circuits whose inputs are bit patterns representing numbers in one code and whose outputs are corresponding representations in a different code. For example, binary to gray code converter has four binary input lines B4, B3, B2, B1 and four gray code output lines G4, G3, G2 and G1. To design a code converter, we use a code table, treating it as a truth table to express each output as a Boolean function of the all inputs. And here in this example, that is for binary to gray conversion, we can treat the binary to gray code table. This is binary to gray code table as four truth tables. So consider this table as four truth tables to derive expressions for G4, G3, G2 and G1. So we have to derive expressions for G4, G3, G2 and G1, and each of these four expressions would contain all the four input variables B4, B3, B2 and B1. Thus, the code converter is actually equivalent to four logic circuits, one for each of the truth tables. So consider the design and implementation of 4-bit binary to gray code converter. For that we have to write here 4-bit binary code, that is write the binary numbers 00000001. So write the 4-bit binary numbers up to 1111. So this is the input to the circuit and output is the gray code. So binary 4-bit binary is the input to the circuit and this 4-bit gray code is the output of the circuit. Now we have to write the corresponding gray code. So binary to gray code conversion we have already studied. So write here write 0, then 0 plus 0 is 0, 0 plus 0 0, 0 plus 1 1. So in this way we have to add, first write the first MSB, then 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, next 0, 0 plus 0, 0, 0 plus 1, 1 and next 1 plus 1 is 0, then 0, 0 plus 1, 1, 1 plus 0, 1, 0 plus 0, 0. Next one 0, 0 plus 1, 1, 1 plus 0, 1, 0 plus 1, 1, 0, 0 plus 1, 1, 1 plus 1, 0, 1 plus 0, 1. Again 0, 0 plus 1, 1, 1 plus 1, 0, 1 plus 1, 0. Next 1, 1 plus 0, 1, 0 plus 0, then 0 plus 0, 1, 1 plus 0, 1, 0, then 1, 1, 1 plus 0, 1, 0 plus 1, 1, 1 plus 0, 1, again 1, 1 plus 0, 1, 0 plus 1, 1 plus 1, 0. Next 1, 1 plus 1, 0, 1 plus 0, 1, then 0, 1, 1 plus 1, 0, 1 plus 0, 1, then 0 plus 1, 1. Next 1, 1 plus 1, 0, 1 plus 1, 0, 1 plus 0, 1. Next 1, 1 plus 1, 0, 1 plus 1, 0, 1 plus 1, 0. So this is the gray code corresponding to the binary code. Now we have to realize each gray bit using the K map. So first of all, draw the K map for the realization of G4. So here the inputs are B4, B3, B2 and B1. So this is the realization for G4. B4, B3, B2 and B1, 0, 0, 0, 1, 1, 1, 1, 0. Here 0, 0, 0, 1, 1, 1, 1, 0. And here also 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. And here these are 0, 1, 2, 3 like that. So for that we will get 0. So either you can enter the 0 here or no need to enter the 0. So only enter the corresponding 1 terms, that is logic 1 terms. 1 0 0 0 is 8, that is 1, then 9, 10, 11, 12, 13, 14 and 15. These are equal to 1. So while realizing this K map, we can consider these 8 squares. So here while considering the column, both B2 and B1, B2 and B1 are changing. And look here the changing variable is B3. So the constant term is B4. So G4 equal to B4. Next we have to realize G3. So for that draw the K map 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So here 0, 1, 2, 3, next is 4. 4 is 1, then 5, 6, 7, 8, 9, 10, 11. 8, 9, 10, 11. These are equal to 1. So other squares no need to enter. So corresponding to this one, we have to minimize G3. So here these 4 squares we can combine. Then for this it is B4 bar B3. And these 4 squares also we can combine, and that is B4 B3 bar, and this is equal to B3 XOR B4. Next we have to realize G2, and for that G2, so here 0, 1, 2, 3, 4, 5 are, that is 2, 3, 4 and 5 are equal to 1. That is 2, 3, 4, 5. And next is 10, 11, 12 and 13. 10, 11, 12 and 13 are equal to 1. So here these four squares we can combine, and it is, here the changing variable is b1, so we can write b2 bar. Here the changing variable is b4, so we can write b3. Then plus, here we can wrap these two squares and these two squares. So here the changing variable is b1, so we can write b2. Then here the changing variable is b4, so we can write b3 bar, and this is equal to b3 XOR b2. Next we have to realize G1. So here 0, 1, 2, 1, 2 are 1. So here 1, 2, next 5 and 6. So here 5 and 6. Next one is this one, that is 9 and 10. That is 9 and 10. And next is this one, this is 13 and 14. That is 13 and 14. So here, while minimizing these four squares, we can combine, and here both b4 and b3 are changing, so here we can write b2 bar into b1, and here also we can combine these four squares, and that is equal to b2 into b1 bar, b2 b1 bar, and that is b2 XOR b1. So after realization, that is after minimization, we got G4 equal to B4, G3 equal to B4 XOR B3, G2 equal to B3 XOR B2, and G1 equal to B2 XOR B1. So we can draw the logic diagram, that is B4 is the output G4. That is G4 is same as B4. Next G3 is equal to B4 XOR B3. So first of all draw the four inputs, B4, B3, then B2 and B1. So next G3 is equal to B4 XOR B3. So here draw one XOR gate. Then B4, that is G3. Then G2 is B3 XOR B2. So here also draw one XOR gate, B3 XOR B2, and that is equal to G2. And next is G1 B2 XOR B1. B2 XOR B1, and that is equal to G1. So this is the logic diagram for the code converter, that is binary to gray code converter. Next is design and implement a 4-bit gray to binary converter. So here the inputs are the 4-bit gray code and the outputs are the 4-bit binary code, and for each binary code, that is for each bit, we have to design a logic circuit. So here this is the gray code bit right up to 15, that is 000 up to 1111, and corresponding to the gray code, the binary code, as first one is 0000, next 0, then add this 0 to this, the next number, that is here 0, then 0 plus 0 0, 0 plus 1 1, next is 0, 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, next 0, 0 plus 0 0, 0 plus 1 1, 1 plus 1 0, next 0, 0 plus 1 1, 1 plus 0 1, then 1 plus 0 1, next one 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1 0. So like that we have to write the remainings, that is for example 1010, the corresponding binary code is write to 1, then 1 plus 0 is 1, 1 plus 1 is 0, 0 plus 1 0 is 0. So like that we have to write. Then next is realization, that is simplify using the K map. First one is B4. So draw the K map. First one is simplification for B4, and here 8 to 15 are 1, that is 8, 9, 10, 11, 12, 13, 14 and 15 are equal to 1. So here these 8 squares we can combine. So here B4 is equal to G4. Next is simplification for B3. Here for B3, 4, 5, 6, 7, 8, 9, 10 and 11 are equal to 1. 4, 5, 6, 7, 8, 9, 10, 11. And here these 4 squares we can combine, and this is for B3. B3 is equal to, here we got G4 bar into G3, and here these 4 squares also we can combine, and that is G4 G3 bar, and that is equal to G4 XOR G3. Next is minimization for B2. 0, 1. Next is 2, 3, 4, 5. 2, 3, 4, 5, 6, 7, 8, 9. 8, 9. And this is 14 and 15. 14 and 15. And here we can combine these two squares. And this is simplification for B2. B2 is equal to, here G4 bar, G3 bar, and here the constant is G2, plus while combining these two squares we got G4 bar G3, here G2 bar, plus while combining these two squares G4 G3, here G2, plus while combining these two squares G4 G3 bar, here G2 bar, and here G4 bar we can take outside, and G3 bar G2 plus G3 G2 bar, plus here also G4 we can take out, G3 G2 plus G3 bar G2 bar, and that is here G4 bar G3 XOR G2, plus this is G4 into G3 XOR G2 bar, and we can write G4 XOR G3 XOR G2, and G4 XOR G3, that is B3. So we can write B3 XOR G2. So this is the realization for B2. And for B1, here we will not get any common or constant terms while doing the K-map. So we have to write each realization bit, that is for each one bit we have to write the corresponding Boolean expressions. That is, for example, for this one we have to write G4 bar, G3 bar, G2 bar, G1, then next plus G4 bar, G3 bar, G2, G1 bar, plus next is G4 bar, G3, G2 bar, G1 bar, next is G4 bar, G3, G2, G1, and next G4, G3 bar, G2 bar, G1, next one G4, G3 bar, G2, G1, G4, G3, G2 bar, G1, plus G4, G3, G2, G1 bar. That is B1 is equal to this one. Now we have to simplify this. Here G4 bar, G3 bar common, G4 bar, G3 bar into, this is G2 bar into G1, G2, G1 bar, that is G2 XOR G1, then plus here also G4 bar, G3 common, this is G2 bar, G1 bar, G2, G1, so that is G2 XOR G1 bar, plus here G4 G3 bar common, and this is G2 bar, G1 bar, G2, G1, so we can write G2 XOR G1 bar, plus here also G4 G3 into G2 XOR G1, and here G2 XOR G1 is common here, that is G2 XOR G1 into, this is G4 bar, G3 bar, G4 G3, that is G4 bar, that we can write G4 XOR G3 whole bar, plus here also G2 XOR G1 bar is common, and we can write here G4 XOR G3, and this one we can write G4 XOR G3 XOR G2 XOR G1, and G4 XOR G3 XOR G2 is B2 XOR G1. So B1 is equal to B2 XOR G1, and B2 we got B3 XOR G2, B3 as G4 XOR G3, and B4 equal to G4. Now we can draw the logic diagram. That is first draw B4. Sorry, the inputs are G4, G3, G2 and G1, and B4 is equal to G4 itself. Next is B3 is equal to G4 XOR G3. So here XOR gate G4 XOR G3 is B3, and next is B2 is equal to B3 XOR G2, that is B3 XOR G2, XOR gate B3 XOR G2, that is equal to B2, and last one is B1 is equal to B2 XOR G1, that is B2 XOR G1 is equal to B1. So this is the logic diagram for the code converter grade to binary. Thank you for watching the class. If you like the classes, please like, share with your friends and subscribe my channel.